So Alisa Knizel, she will talk about stationary measure for the open KPZ equation. Please, the floor is yours.
Okay. Yeah, thank you very much for the invitation. It's a pleasure to speak here. So I'm going to talk about our joint work with Ivan Corwin and a little bit about joint work with Konstantin Matetsky, which we are like wrapping up right now. So the story is about the stationary measure for the open KPZ equation, and so it begins with the like main character for the talk, the KPZ equation itself. So the Kardar-Parisi-Zhang equation, which was introduced to model the surface growth in 2D. So this is the equation, and it describes the evolution of the height profile of the surface growth. So h is the height. It depends on two parameters, t and x, time and space parameter. The time will be positive for us, and on the right hand side, the like three terms, they describe the three basic mechanisms of the growth of the interface. So the last one, psi, is the white noise, which represents the like random kick. So the surface like goes up at different like random spatial points independently. Then there are two other terms. Like the second term is the first term is the smooth mechanism, and the most important term is the quadratic term, which corresponds to the so-called lateral growth. So the growth, the growth which is like occurring at different spatial point in such a way that like the interface like grows like this. So this is the like very heuristic description of what the KPZ equation look like. And in this talk and in our work, we focus on the so-called open KPZ equation, which is amounts to considering this equation with the following boundary conditions. So we impose this equation on the interval, the 0-1 interval, and we have the boundary, the von Neumann boundary conditions on the left and right, which are parameterized by two parameters u and v. So on the left, it's u, and like for the the way we parameterize it is having minus v on the right hand side. So this is the this is the main object that we work with, and a natural question to study is the like understanding of the stationary measure for this equation. So like the this equilibrium that the system will tend to as time increases. So what does it formally mean? So there's like a very long story about the like very long and very deep and interesting story about the solutions to the KPZ equation. For us, we are working with the following so-called Hopf-Kohl solution in our work. So if we so this is defined in the following way. So we consider first the stochastic heat equation, so here we need to consider the so-called inhomogeneous Robin boundary conditions. So so this is like here we see like on the first line the stochastic heat equation, and so the like the way to relate it to the boundary conditions that we have for the KPZ, we need to impose the following conditions for the boundaries here. So we have the so we have like for convenience we have here this this constants minus 1/2 in the like left and right boundary subtracted. So so like formally, the Hopf-Kolk solution to the open KPZ equation is defined as the logarithm of this function z, which solves the stochastic heat equation. And this is like, and this is the object which we'll be working with. And I'm not gonna go into the like technical details about like about the notion of the like further about the notion of the solution here. So so this is what we work with, and now like what it means to be stationary. So like this equation, the KPZ equation, there is a drift at 0. So here, like in order to define a stationary measure, we need to subtract the height profile at 0. So so this is the definition. A stationary measure for the open KPZ equation is the law like such that the process htx minus ht at 0 as a process in x is independent, is time independent. So this is the notion of stationary measure, and the question is how identify such measures for this equation. So the KPZ equation itself is considered with different type of boundary conditions. So one can work with KPZ equation on the whole real line, with KPZ equation with the periodic boundary conditions, with half line. So when you consider, say, the interval from 0 to infinity, and also this this case that we are working with, the interval. So in the case of the periodic boundary conditions and the full line, the question about the stationary solutions was investigated quite long ago. So in the physics literature, the stationary measure is Brownian, and so it's so it was first indicated in the physics literature, and then in the works of Unaki-Castell and Harem and Mattingly. So in the case of the whole line, the first work, and the periodic boundary condition in the second one, it was shown that this Brownian solution is the unique stationary measure for the corresponding KPZ equations. So the question about the interval and the half line remained open, and so interestingly, there were not even the concrete and there were like essentially no predictions even in the physics literature about how this solution should look like. And so and also like in general, there was expectation that like once the solution is identified, it should be unique as well. But so this is like the also another story that should have been investigated as well. So like a couple of more words like about this case that we consider the so the interval is a very natural is a very natural is very natural to consider in this situation, not from just a point of view of the KPZ equation, but also from point of view of many applications where the KPZ equation arises, and it arises like precisely in the form of the KPZ equation on an interval. Okay, so the way we approach the problem is through considering the discrete model, which is called the open asymmetric simple inclusion process, which has an observable, which is going to be like also called the height profile, and after considering a certain scaling limit, the height profile of the open ASAP will converge to the solution of the open KPZ equation. And so like in such a way, we will get the information about the solution to the stochastic PDE. This discretization that we consider is the following Markov chain, Markov process on configurations of points on the interval. So here the interval is pictured in the bottom, and the red dots correspond to the particles on this interval. So the possible locations of the particles are the integers from 1 to n. So those are the labels of the location. So here n is 10. So those are like the black dots in this figure. So now the particles, the evolution of the system is the following. So the particles are allowed to jump to the right and left by 1, subject to the condition that the corresponding side to the left and right is vacant. And also we have the reservoirs, which are pictured as these gray squares on the left and right, and the particles are entering the system and exiting the system as well, with the same exclusion principle that they can enter only if the corresponding site is the corresponding neighboring site is vacant. So all this is happening according to some weights. According to some weighting times, exponential weighting times, which are given by the rates, which are parameters of the system. So the parameters here are alpha, gamma. Those are the rates of jumps for the left reservoir, beta delta, the rates of jumps for the right reservoir, and so the particles are jumping within the interval with the rates q and 1. So like overall, here we have 6 parameters for the system. So the size, this is the large n parameter, and then these parameters for the jumps, alpha, beta, gamma, delta, corresponding to the reservoirs, and parameter q. So those are the parameters. This is how the evolution on the configurations is organized. So now, what we will be concerned with is the following function, the height profile corresponding to configuration of the system, which is pictured here on top. So this is this zigzag path, which is the graph of this height profile, and the way one can construct a correspondence between the configurations of particles and such height profiles is through the following geometric recipe. So if we start from some point on the left boundary here, above the reservoir, then the construction of the zigzag profile goes as follows. So it consists of steps of segments with slope 1 or -1, and the sign of the slope corresponds to the fact whether we see a particle present like underneath the endpoint of the segment or not. So here, like when we start from the left, we first see the red dots. So there's a particle there. Therefore, the profile goes up by 1. And then like there is no particle, there's just black dot. So we go down by 1. Then there are 2 red spots, 2 particles, we go up by 2, and so forth. That's how the height profile encodes the configuration of the particles. So as long as we fix like where we start on the left, which is some like technicality, then like we have a bijection between these height profiles and the configuration of the particles. So in such a way, we can also talk about the Markov process on this zigzag paths. So this is the story about the open ASAP. So like formally at 0, so on the left boundary, we will normalize the height profile to be -2 times the quantity which is called net current. It equals the number of particles that enter into the site 1 minus the number of particles exiting from site 1 up to time t. And like formally, like what I was talking about, this bijection, like one can define the height function here. So it depends on n. We have this subscript in the notation. Through this formula where tau I are the so-called occupation variables, so they are equal to 0, 1, depending whether we have a particle present at the corresponding site or not. So this is the formal definition of the height function. So now what about the stationary measure? So here, so the open ASAP is an irreducible continuous time Markov chain with finite state space. So there's a unique invariant measure which we denote by pi, and the notation that we'll use is so the expectation of some function f will be denoted with this angle brackets. And is defined in this form. So this is the expectation with respect to this invariant measure. And in particular, we will be interested in the following quantity, which is called the stationary current. So like the like how many particles are passing through a given, like a normalized amount of particles passing through a given site on the interval, which is the following quantity. So it's the expectation of this like difference. So this difference corresponds to like the since we are working at stationarity, we can only we are like we can focus like here on the like how many particles are entering through site through the first site. So here we have just like the like normalized net amount of particles passing through the first site. This is what is written on the like inside of the brackets here. Just like tau 1 is corresponds to whether like the jump from the reservoir is allowed or not. So this is what we have inside the brackets here, and we also like we have this normalization 1 minus q. So this is the stationary current, and it was shown that the stationary current there is a limit as n goes to infinity of this quantity, which is called J, and like moreover there's the following phase diagram corresponding to the behavior of the limit current J depending on the parameters of the system. So here the coordinates of this diagram are denoted by rho L and rho R. Those are like some rho L and rho R the so-called densities at the left and the right of the interval. So there's like a precise formula for those quantities in terms of the parameters of the ASAP, so alpha, beta, gamma, delta, and Q. So it's a little bit lengthy, so I didn't put it on the slide. So so rho L and rho R, they specifically so they depend on the parameters of the system. So now, depending on this on rho L and rho R, there are 3 regions, and for those regions there are different formulas for this limit current J. So there are 3 phases: the maximal current phase, the high density phase, and the so-called low density phase. Like physically speaking, they correspond to how the process of like particles moving from along the interval is organized. So the maximal current phase is like when the particles are moving like most efficiently. So the left and right boundary, they do not like create any slowdowns in the movement of the particles. And like the high density and low density phase, they correspond to like the fact when whether you have an overflow of the particles from the reservoir or like underflow. So this is the like how the phase diagram is organized. So it was first studied like this phase diagram under like special conditions on the parameters in the seminal work by Derrida, Evans, Hakim, Pasquier. Then in the physics literature by Sando, and for general case of the parameters, it was this phase diagram was shown and proved in another seminal work in this field by Uchiyama, Samoto, and Vadati in 2003. So this is the description of the behavior of the open ASAP at stationarity through its current. Okay, so now like what about the KPZ equation? So the KPZ equation appears once we like zoom into this picture into the triple point here. So the point in the very middle where all 3 regions, like 3 different phases for the open ASAP meet. So this is done through the so-called weakly asymmetric scaling. So in order to be consistent with our boundary conditions, so like which are parameterized by U and V, we need to scale the open ASAP in the following way. So we will be looking at the parameters rho L and rho R around 1/2. So going back to this picture, 1/2 is exactly this like where this triple point occurs. So we need to look around 1/2 in the window of the size 1/square root of n. So this is this is what we need to do, and in order to achieve that, we will look at the open ASAP. So again, this rho L and rho R, they are just explicitly written in terms of alpha, beta, gamma, delta. So what we will do, we will consider parameter Q to tend to 1 with the following speed. So it's going to be exponential, and the exponent is so it's so -2 is 2 is for convenience here, so it's 1/square root of n. That's the speed. And then the parameters alpha, beta, gamma, and delta, they need to be of this precise form. So there are just explicit formulas in terms of Q, U, and V that we fix. So once we fix the family of open ASAPs with these parameters, we will send n to infinity. We will consider the rescaled height function. So the rescaling is through 1/square root of n. For our purpose, we will work with the stationary profile. So here we have Hn, which depends only on the space parameter x. So the space is also scaled linearly with n. I have omitted the dependence on the time, since it's since we are focused at the stationary, since we focus at the stationarity. However, this connection between the ASAP and the KPZ equation, this solution to the KPZ equation is much more general. So so there are certain conditions on the initial data in the works of it was like first discovered and worked out in a seminal work by Bertini and Giacomin, and then in the works of Corwin and Shen for the open for the interval, and like for more general for the more general case of the parameters in the work of Pariach. It was discovered that there is that the properly scaled height profile of the open ASAP under this weakly asymmetric scaling converges to the solution of the KPZ equation, and so that's where the connection between the open ASAP and KPZ equation takes place, and that's what we heavily rely on in our work. So here is like the summary of the main things that we do in our work with Ivan Corwin. So like first we construct the stationary measures for the KPZ equation that we call WASAP stationary measures. So for general parameters u and v, we construct them as the limits of the scaled height profiles of the open ASAPs. So we check that we check that working with working at stationarity like fits into the framework developed by Bertini and Giacomin, and then by Corwin and Shen for the interval, so that there's this a link between the height profiles of the open ASAP and the solution to the KPZ equation. So that's the first part, and the second part is the characterization. So once we have the construction of this WASAP measures, this WASAP stationary measures, the question is how how to describe them. And in our work we have a description, an explicit description through the multi-point Laplace transform for these measures. So this is the two main outcomes of our work. So the statement of the theorem that we prove is the following. So the first part amounts to the construction for general U and V. So this is the so we need to show show tightness here and describe the convergence along the subsequential limits. So this is the first part. Then the second part, which we have, is the following statement about the coupling. So the statement that about the sandwiching of the WASAP solutions that we get for different time and space points. So this is so this is like a more technical part, which we use to show that the calculation that we obtain indeed uniquely determines the limit. So this is the third part that we have, which requires us to consider only the case where u plus v is greater than 0, which corresponds to looking at the which corresponds to considering only the upper triangle in the phase diagram for the open ASAP. So this is the condition that we need to have in our work in order to get the description in terms of the Laplace transform for the multi-point Laplace transform for the wave-step stationary measures, so we get this description in terms of the Laplace transform, and then the second part about the coupling helps us to ensure that this is this Laplace transform uniquely characterizes the limit object. So this is the main result of our paper, and like to give you like a flavor how it looks like. So the multi-point Laplace transform, like under these conditions, when we ask the parameters u and v to be positive and take the parameter c in some interval, then like this Laplace transform, the expectation of the exponent of minus c times the height function at 1. So so this height function, the limit height function at 1 records the net height change across the interval. So so this is the form of this expectation. So here we see the ratio of two integrals, and the integrals involve different products and ratios of gamma functions. So this is how in general the formulas that we get for the multi-Laplace transform look like. So I'll get back to this in the very end of the talk as well. So as we see, like from this formula already, the nature of the stationary measure for the open interval is much more complicated than being just Brownian in the case of the KPZ equation on the whole line and the KPZ equation with periodic boundary conditions. So this is the characterization that we obtain, and some natural questions that are remained about the stationary measure is, of course, the uniqueness. So we construct this wave-step stationary measures for general parameters u and v, but our approach doesn't say anything about like whether there are any other stationary measures. So this is what is addressed in our work with in the joint work with Konstantin Matietsky, which we hopefully will post like very soon. So under some technical conditions again that we have to make about the parameters u and v, we prove the uniqueness. So in principle, the uniqueness is expected for there's a conjecture that the stationary measure is unique for all choices of the parameters u and v. So like in some region, we are able to show the uniqueness. So this wave-step measure, so the measure which comes from the consideration of the open A-step, is the unique one. Another question is the probabilistic description. So we have this characterization through the Laplace transform, but it would be nice to have, so it would have been nice to have a more direct way to describe the solution as like certain process with some properties. So this is something which was like worked out in the works by Rick Kuznetsov, Wang and Veselovsky, and Barakan and Liodusau in the physics literature. Like again under certain, so it's in the physics literature. So in the work by Barakan and Liodusau, the like form which I will describe now is conjectured to be valid for all the parameters u and v, and in the mathematical work, in the rigorous work by Rick Kuznetsov and Wang and Veselovsky, it was shown that this description indeed like fits for certain range of the parameters u and v. So what's the description? So it turns out that the multi-point Laplace transform that we have can be inverted. So that's what have been done in these works. And the process has the following structure. So it's a sum of certain process X and an independent Brownian motion. So here we need to have this this rescaling with the factor of 1 over square root of 2. So the process X has an explicit description through its Radon-Nikodym derivative. So it has a so this process is absolutely continuous with respect to that of a Brownian motion with the diffusion coefficient 1/2. So there's an explicit formula for this Radon-Nikodym derivative, and that's how the process X is is constructed. So this is the description that is now available for the stationary measure on the open KPZ equation. For the open KPZ equation. So I will pause now for any questions, and then I will talk a little bit about the methods that we use in our work.
So these two references that you gave are with the Robin boundary condition. So open KPZ.
Yes. So like in these two works, like the Laplace transform that we have constructed is inverted. So in the physics literature, like this process has appeared that is described on the slide, and it's conjectured to be the unique solution for all parameters U and V. And in this mathematical work, it was shown that this indeed this process inverts our Laplace transform for a certain range of the parameters U and V.
And is there an intuition of this factor of 1 over square root of 2?
I don't have a good answer to this question, like why Brownian motion appears in this way here.
Okay.
May I ask a question? Yeah, so you mentioned also, I think, half open KPZ with half open intervals. Just that sometimes people consider that. So, do you have ideas about what is the situation of invariant measures in that case when you have a half open interval?
So there's a recent work by Corwin and Barakan where they answered this question, and like there they proceed like through the intuition behind like how this like process X like here is described. So we described like through like as a certain like so this process is described through certain like path integrals. So in their work for the half for the stationary measure for the KPZ on the half line, they like instead of working with the open ASAP, they work with the polymer model and use this approximation and like counting paths there to get to the stationary to get the description of the stationary measure in that case.
Okay, thank you.
So like now in like for the half space, there's an alternative methods as well developed like very recently, like how to attack this question about the stationary solution.
Thank you.
Okay. Okay. So I will say a couple more things about the methods that we use in this work. So the key technical ingredient for us is the following formula from the work of Brick and Veselovsky, which describes the joint generating function of the stationary distribution for the open ASAP through an expectation with respect to to some Markov process, which is called the Askew-Wilson process. So here, like on the left in this equation, we have this joint generating function. So tau j's are again this. I should remind you the occupation variables. So they are 0, 1 for the occupation variables corresponding to the sites on the interval. And on the right we have this process y. Which I'll describe like on the next slide. So this connection, so this process is called Askew-Wilson process because its marginal and transitional probabilities will be defined in terms of the weight function for these for the classical Askew-Wilson for the classical orthogonal polynomials from the ASCII scheme called Askew-Wilson polynomials, and this connection to the Askew-Wilson polynomials was first established in this key work by Uchiyama, Samoto, and Badati. However, the way the Askew-Wilson process, the Askew-Wilson polynomials like enter the formula here is the most best suited for the purposes of our work, like when we take the scaling limits. So this is the kind of like key formula that we use. To give you a flavor how this process is defined. So the Askew-Wilson process, so here I will define the Askew-Wilson process, which is needed in this formula. So we already have we already impose the weakly asymmetric scaling. So the parameters of the functions here will be written in terms of Q, which was like the expectation of -2 divided by the exponent of -2 over square root of n, and UV are our boundary parameters. So so here the Markov process that we use is defined through pi, the marginal distribution, and p, the transition probabilities. Like where the function AW is the weight function for the Askew-Wilson polynomials, and it's written in terms of products of Paget-Gamma symbols. So the Paget-Gamma symbol is this product in the bottom of the slide. So this is so like as you see, so that's in terms of taking the scaling limit. An important part is to be able to control the limit behavior of these Q Paget-Gamma symbols. So this like products when Q goes to 1. So this is what we encountered on our way, and so this is the like something that we worked out in a great detail. So for the purpose of our work, we needed to have like a very good control of the behavior of these Q Paget-Gamma symbols. So in this proposition here, we compute the expansion for the logarithm of these Q Paget-Gamma symbols. So here this parameter kappa will so our Q goes to 1, so kappa goes to 0. And what we need to do is we need to have a very good control of the error term, both in terms of parameter kappa and also parameter z. So z is the like exponent in which the Q enters the Q Paget-Gamma symbol, and the main contribution is given by these two lines on top of this slide. So yeah, and in the formula where we have where Q enters the Q-Page-Gamma symbol with without the negative sign, we have the gamma function which appears. Yeah, so essentially, if we look at if you look at this first line, so our kappa will go to 0. So the first two terms, they actually are blowing up. Yeah, so in order to have a meaningful limit, what happens is that they will be compensated with other terms in this so in this product. So yeah, so we carefully check that all this is canceling out. So what we will be working with in the end, coming from the Page-Gammers with no negative sign, is a product of gamma functions. So that's exactly this last term that we see on the first line. Yeah, so this is the main contribution that we'll have from those Page-Gammers once we take the limit. So that's how the gamma functions appear in our formulas, and that's where you've already seen them in this multi-point Laplace transform that I've shown you in a special case. So that's how the gamma functions appear. So yeah, so working on this proposition was very fun. So we've learned quite a bunch of tools from analytic number theory. Yeah, and this type of question was studied in many works in the number theory community, but the type of the control on the arrow that we needed in our work was stronger and different compared to the interests in that community. So yeah, so that's so we needed to address this question in great detail in our work. Okay, so yeah, so this is the key technical component needed for taking the asymptotics, and quite interestingly, there's a sort of a more compact way how you can write the formulas for the multi-point Laplace transform that we have, using another Markov process, which we call the continuous dual Hahn process. Yeah, so we need some technical assumptions on where the parameter s, the time can live. So yeah, so we define this large capital C to be a certain range, to be in a certain range depending on parameter u. So now we define the marginal distribution, this mathfrak Ps to be written in this form. For u and v positive, for general u and v, this process, the form of this process is going to be more complicated because it will the marginal and transitional probabilities will have not only continuous part but also atomic part. So this is what I have on the slides is only an easier case when you have only continuous parts. Okay, so this is the marginal probability that we'll have, and then the transitional probability mathfrak PST will be determined through another function. So this is the function which is the weight function for the dual continuous. For the continuous dual Hahn polynomials, so in our notation, it's the CDH function. So it has this form of a products of gamma function, of products of different gamma functions. So again, similarly to the Askew-Wilson process, we define the transition probabilities through this weight function. And then, so if we properly define this process and check, so we check on our work that in this way we obtain a Markov process. Then like the way our formula for the multi-Laplace transform, multi-point Laplace transform for the way substitution measure is written is given here. So the Laplace transform on the left, this expectation is written in terms of the expectation with respect to the process T, this continuous dual Hahn process. And like in the bottom we have this a scaling factor, which also is an expectation with respect to this process T. So that's like the form of the multi-point Laplace transform that we get in our work that uniquely characterizes the wave substationary measure in the range of the parameters u plus v is greater than 0. Okay, so I think I'll stop now, and answer any questions you might have. Thank you very much for your attention. Mm-hmm.
Thank you very much, Alisa. Are there questions or comments from the audience? Let's see.
So I have a question. Yeah. Mm-hmm. Let me think. Okay, yeah. When you mention this characterization of the invariant measure as the sum of Brownian motion plus something else, right? Do you know if this process has exponential moments? Because in principle Brownian motion has exponential moments because it's a Gaussian random variable, but and this guy is absolutely continuous, but that's not in principle imply that that it will have the same tail behavior of Gaussian random variables, right?
Mm-hmm. Yeah, that's a very good question. I haven't thought about it, so I think, like, given the formulas that we have, it's possible to answer this question. I just haven't thought about it.
Okay.
Mm-hmm.
Yeah, I mean, for our point of view, as you may know, we have this very different approaches to KPZ equation, which are very much analytical. Mm-hmm. and for us, for example, existence of exponential moments is very important. Mm-hmm. And our methods only work on a certain region of parameters, so it will be very interesting to see if mm-hmm. outside this region of parameters, the reason why it doesn't work is because the mm-hmm.
Yeah, it's a very good question. I haven't worked out it, but it's like since the formula is quite explicit, and also I think through Laplace transform you can also access this type of question. So mm-hmm. So I think all the ingredients are there to compute.
Okay. Mm-hmm. Yes, thank you.
If there are other questions? Okay, doesn't seem the case. So we can thank.
Maybe if you allow me, I would like to make a last question. Yeah. Mm-hmm. So you mentioned your work with Konstantin. Mm-hmm. So what are these conditions that you mentioned? So under which conditions this uniqueness?
Well, we need the conditions similar, which are similar, which are here. So so essentially, we need we have the result about the uniqueness right now. So though we think that we have a method how to do it for at least all the region u plus v greater than 0. So the the result that we have now and which we are wrapping up is the same conditions which appear in this work, where the conditions for which we can rigorously invert the Laplace transform.
Okay.
Yes. So yeah. So that's the So that's the condition that we need as of now. But But we think that we can get rid of this. That we can get rid of this condition.
Okay. Thank you.
Let's see. So if there are no more questions, let's thank Alisa again.
Thank you.
Thank you.
Thank you very much. And we update next Wednesday. Next same time, same place.
Thank
Bye-bye.
you so much. Yeah.
Bye. Thank you.
Thank you. Bye bye.
Thank you.